Larry is really good computer science. He and his wife were I think, recruited. Is it true? Yeah, to come to WSU in order to enhance the kind of the experienced chemical, computer scientists, and they are really front runners in the country in their particular areas. So go ahead and talk to us about a little bit about yourself, maybe your family.
So can you hear me in the back? Okay. Do I need... So I guess a little bit about myself. So I got my PhD in 1991 from University of Illinois. My wife is Diane Cook, who's a superstar here in the department. We both do work in AI and machine learning. And in particular, I do a lot of work in graph mining for lots of different applications, but one that I do a lot of is, I guess, defense-related projects. And this insider threat detection was a part of that. Actually, this came out of mostly a DHS project, but the same tools that hopefully you'll be able to use today apply to lots of other domains. And the main reason is because graphs are a very general data structure, so you can pretty much represent anything as a graph. And if you do it the right way, then you can find some interesting patterns and anomalies in that graph, which could lead to identifying bad behavior. So before I get started, if you go to this website, there's some tools here. So my slides are there. I'm going to have 3 exercises to go through. And so that exercises link is just the instructions in the PDF. I kind of tailored this towards the Amazon workspace, Linux distribution, which has, a C compiler and everything. So these first 2 pieces of software, Subdue and GBAT, are C programs that you'll need to download and compile. And again, there are instructions for doing that. I'll go through it once we get there.
Yeah.
Oh, I'm sorry. So go to my webpage. Oh, yeah, there. Go to my webpage and then type the /CySER.
So the webpage you can get from your faculty profile at ECS?
Well, this is just where I hung this information off of. I mean, it could be anywhere, but yeah, it's a subdirectory off of my main homepage from WSU.
So if you go to WSU ECS, Technical Engineering Computer Science, look at faculty, go to Larry Holder, and under there he's got a website. So you go there, and from there we're going to. I'm here now.
Oh, there's no public access to this link, so you're not going to be able to find this link on the web somewhere. You'll have to go to it directly. And it has to be exactly this. If you put like school.ecs, what's that?
We just need to type this in there.
Yes.
Okay.
Type that into your browser. It should get to.
Okay. Put down there.
So the one tool that we'll need that is not mine is a graph visualizer, and you can go to this website to find it. But you'll see there, if you're following along, using the AWS. Go to the download link, you'll see if you do this, you type this into your AWS Linux distro and supply your password, it will install that for you. You don't have to download the code. You can if you want. So I'll go through this again a little later, but for those of you who get a head start. Okay, so what am I going to talk about today? I'll give a brief introduction of what an insider threat is, and then I'll talk about the two main tools that we use to analyze the data from various domains. They're represented as graphs. So first we'll look for patterns in the graph, and then we'll look for anomalies in the graph. And the anomalies are a kind of a special breed of anomaly that we look for. It's not noise, it's not an outlier, but I'll explain more about that. And then I'll show some examples of insider threat detection that we've done, and let you walk through one of the examples that we use. So I don't know, some of you are probably better experts at insider threats and cyber security threats and breaches and so forth. But you can go pretty much anywhere and get some pretty dire statistics. This one that I found here, and works. So just from 2020 to 2021, might be hard to read, but the number of breaches went from 1,100 up to 1,800. And so that's been increasing over time. Strangely, the number of victims is going down, which is probably because people are compartmentalizing their data better. But unfortunately, the breaches are not getting better. And there's a lot of ways that these breaches can occur. Probably, there's kind of two different insider threats. One is the insider who is clueless, and then there's the insider who's malicious. And so a lot of times the clueless insider will basically ignore security policies and do stupid things, and someone will gain access to the systems through them or through their errors. But of course, there's also malicious actors who have an axe to grind with the company, or they're in debt, they're just depressed, and they want to take it out on someone else. And so they have certain security access, and they exploit that to steal information, commit fraud, or actually leak that information outside the organization. And of course, there's the standard cybersecurity threats that we're constantly bombarded with, and a lot of them eventually work. So, one interesting statistic. So this is from this ITRC, the IDTheftCenter.org, and one of their reports cites that of the security breaches last year, 35% of them were insiders. And so, it's one thing to harden your enterprise to outside attacks, but you're always going to be faced with the insiders, again, either making mistakes or maliciously doing bad things. So everybody wants to be able to detect insiders and ideally even predict that someone is at risk to becoming an insider. And so that's really the main task we're trying to address here is, whatever data you're collecting about your organization, how can you represent that data, analyze it, and identify insiders, at least be able to identify that they have become an insider threat, but ideally be able to predict that they are at risk of doing bad things. So that's our goal for insider threats. So what are the existing approaches? And so these are basic automated approaches. There's plenty of, if you go to, probably the CERT, the CMU's Software Engineering Institute, their CERT Institute has this document that has about 100 things that you're supposed to do to stop insider threats. But most of them are things like, make sure, people don't share their passwords, and make sure people don't access systems they're not supposed to, or give somebody else access to a system they're not supposed to. And those are good policies, but ultimately, especially for a malicious person, they're going to try to circumvent that and pretend that they look like a normal person, but they're doing something slightly different than they have been. And so we'd like an automated way of doing that. So you're collecting a lot of data and you're analyzing it in some way. And so these are kind of the three main ways that this automated process goes. One is, of course, to monitor external interactions. So the classic insider threat is somebody who leaks information outside the organization. And so if you are monitoring, the firewall or the connection to the outside, then there are tools for detecting when people do bad things. Another main way of doing this is to come up with behavioral profiles. So, if you work at an organization, they can collect all of your data, social media, emails. There's not a lot of privacy there, and they can build a profile about you. What do you commonly do from day to day? And then when your behavior deviates from that routine, then that is something to look at to see if potentially you're heading in the direction of an insider threat. And another one is just analyzing people's movements, which is more, a lot of times it's physical movements throughout the facility. So, if you have a classified area, some people, if you're going to badge in and that's all going to be tracked, some people will piggyback on others and get into areas without actually swiping in, which is a big problem. So, again, you can analyze people's movements throughout the organization, and you can analyze what they're doing. So if they're accessing a system, that's reported, and then if they're not supposed to have access to that system, that would raise a red flag. And a lot of times, this data is collected. There's probably 20 different machine learning algorithms that have been applied to this data to try to do both detection and prediction, and all have varying success. And I think the main weakness that a lot of these approaches have is they're really statistical in nature. They're saying, okay, Larry accessed the database, on a Saturday. Does he normally do that? Maybe I do, maybe I don't. Maybe I never do it on Saturday, but I had a big report due and I really had to access it. And so it was a perfectly legitimate reason for doing it, but it was different from my routine. And so the question, most of these approaches would raise the red flag and say he's doing something he's never done before. This might be bad. But if you're a little bit more savvy and say, oh, well, Larry's got a big, presentation on Monday, and whenever he has a big presentation on Monday, he works on Saturdays. And so with a little bit more context, it becomes normative behavior. And so that's really what we're getting at with this graph-based approach, because the graph allows you to not just look at, my access patterns, but also relationships to other things like what am I working on, and when is my next presentation, and you can build a richer context around your activity, which can help eliminate a lot of false positives, which are the bane of security, because nobody likes your AI system to keep saying, Larry's an insider threat, Larry's an insider threat, and the security check it out and say, no, he's not, and they eventually don't look at the AI system. Too many false positives. So here's an example, and we'll actually run this later. This is a synthetic example, but it's built on top of actually a passport processing office, I believe it was in Hong Kong, that was having a lot of problems. Their main problem was that the office staff would access the passports of celebrities in order to figure out where they are. And then they would tell tabloids, hey, big celebrity, Taylor Swift is in the Caymans, so they all go to the Caymans and try to catch her or something like that. And so they were having these problems. And so the question is, how could they detect that, for example, the frontline staff shouldn't be accessing the database in terms of looking up information, but they do access the database to create cases and things like that. And so you really need a lot of contextual information. So this is kind of the situation over here where the idea is that this is the stuff in dark here is what we call a normative pattern. That's what normally takes place. But we have this one unusual access where the frontline staff is reviewing a case and looking it up on the database, and they shouldn't be doing that. And so, they're obviously reviewing cases in the database is something that people do all the time. And so we want to be able to detect it, but in the context of what's normal. In other words, in this case, it's pretty obvious if frontline staff accesses the database, that's perfectly fine. But if they do it in this context, then it's a breach of security. Another example over here is that so another example is, when in this passport office, once there was, an application, it would go to this approval officer, and the approval officer would assign it to a case officer. The case officer would review it, report back to the approval officer, and the approval officer would make the final case. And so here the idea is that the approval officer assigns the case to this case officer, but then there's another case officer that makes the recommendation, one that wasn't assigned to the case. And so that is not what's supposed to happen. And so, but certainly this is a real case officer. Case officers make these recommendations, but it's in the context of the fact that another case officer has already been assigned. And so that's kind of what we're trying to get at, is that when you represent the situation as this graph and you include kind of this is what normally happens, it's a lot easier to detect when something goes wrong, as opposed to just looking at the red part and say, well, we have a case officer who's recommending that the case be accepted. Well, case officers do that all the time. It's only an anomaly in this context of the normal behavior. So that's kind of where we're going with this is, when we collect data from a process like this, we want to first identify what are the normative patterns, what normally happens. And then once we have the normative patterns, then we can look for anomalies to that normative pattern. And so again, we're not looking for statistical outliers or noise, but we're specifically looking for something that's happened in the context of normal behavior that we don't normally see. So, questions? Feel free to ask questions. So there's kind of two steps to this. And again, one is to find the normative patterns and the one to find anomalies. And finding, well, both of those kind of fall under graph mining, but generally when you think of graph mining, you're usually thinking of finding patterns in a graph, not extracting knowledge from the graph. So let me talk a little bit about graph mining. So, graphs are everywhere. Not all of these apply to insider threats, but a lot of them could, in terms of representing the power grid as a network, looking at social media, monitoring the web page accesses, the internet, or the intranet within an enterprise. All of these can be represented as a graph. And again, the goal is to identify what's normative in here, and then in the context of that, what is an anomaly. The main challenge with all this is that these graphs are huge. And if you took my data structures class, you know that most graph algorithms are crazy hard. I think called NP complete or exponential running time, whatever you want to call it. And so 2 to any of these numbers is probably one of those more atoms in the universe number, and you just can't solve it in fast enough. So a lot of the work we do in graph algorithms is to instead of making them optimal algorithms, we make them approximate algorithms, and that way they run faster, but at the cost of perhaps missing some of the patterns we want. But the main thing we're faced with, it doesn't matter whether this is Facebook or the web, or this is WSU or your favorite government agency. We've got tons of entities, whether it's websites or people. We have tons of links, whether it's hyperlinks or likes or whatever it happens to be. And not only is there's a lot of data here, but the data, all of these graphs are dynamic. They're changing over time. And so the challenge is, to deal with this scale of data, not only in its volume, but also its velocity, which is how fast it's coming in. And I like to show this. This is a little movie that shows some tweets coming in. And we're basically running our algorithms in real time on these to find normative patterns and anomalies. But so let me run this. So what's going on here is that when somebody retweets a tweet, so say person B retweets a tweet of person A, we now know that B follows A. And so the links that are forming here are links from person B to person A. Or the reverse would be A is followed by B. Doesn't really matter which direction we represent it. But we don't necessarily know that somebody follows someone else until they retweet a tweet from that person, and we know they follow them. And so you can see what's going on is we're basically getting a bunch of random tweets that or retweets that are fairly isolated, but we are finding a few tweets that are being retweeted by a lot of people, and so we find out that this person is being followed by lots of people. And this isn't an anomaly or anything, but this is kind of what you have to deal with in terms of the data. Again, not just the static graph, but the fact that it's changing over time. And I don't remember what that tweet was, but it's a very popular one. And then this, of course, is just a sample. Twitter doesn't allow you to, scrape all of their tweets, but they do give you an interface that allows you to sample the tweets in real time according to certain keywords or something like that. So we've got this graph that you can now hardly see. And the question is, so what's normal and what are anomalies here? So the first thing is, what's the typical pattern in this Twitter graph? Well, the typical pattern is a person who's followed by a lot of other people. In this case, maybe 4 to 5 people. In some cases, just 2. And so that's the first step, is to identify what's normal in this graph. And then the next step is to identify the anomalies in this graph. So, for example, here's a user that has two followers, but only one of the users follows another user. So it's basically saying I've got two followers. One of them doesn't follow anybody else, and one of them follows one other person. And that's pretty unusual. You know, most people follow lots of people. Yeah, obviously it could be that we just didn't observe the retweets that would let us know that these people follow other people. But if this was, an authentic view of the data, then this would certainly be an anomaly. Another one is 3 users followed by the same user, but no one else. And so, again, that's pretty unusual that you would only get 3 people, as we saw before. Usually, you're getting 4 to 5 people following you. And so, why would you care about this? Well, you might be, read the news. You know that it would be nice to be able to identify the bots that are in Twitter, and these kind of unusual patterns could be those bots. Maybe not an insider threat, but definitely you could think of it as a fraudulent presentation. So that's just an example of what we're trying to do, and also drive home the fact that most of this data is highly dynamic over time. And so you have to deal with that factor as well. So a little bit of, I guess, boring stuff about graphs, just to make sure we have our definitions right. So we talked about the fact that graphs are dynamic. So we want to first talk about static graphs. And when I say the word pattern in a graph, I'm saying, if you look at this graph, what are the common patterns in that graph? And then once you have those, then you would say, okay, what's an anomaly? So this is where we differ a lot from what you normally see in the literature, is that a lot of people go after outliers. They're just saying, this is unexpected. It's like, well, okay, that's unexpected, but should I care about it? And so then I would say, well, it is expected. So even though it changes, in context, you get a different color node everywhere, it's not unusual because I observe that noise in the data all the time. And so our definition of anomaly is specifically in reference to a normative pattern. So that makes it not just an outlier. And it's an unexpected deviation, which means it's not noise. And so in order to find these kind of anomalies, we have to find these normative patterns and then look at all of the, kind of the structure around them and see if there's something that doesn't follow noise or an outlier pattern. And then when we go to dynamic graphs, there's kind of 2 ways to handle them. One is to take a static snapshot over time, which is pretty simple, but it usually is not very efficient, because as these graphs get big, you can imagine these snapshots keep getting bigger and bigger. And if you're trying to process multiple of them, it can take a while. The other approach is to represent a graph as a stream of changes to the graph, which is a little bit more efficient. Usually what you do is you collect a bunch of changes, you wait an hour and collect all of the changes, and then you build a static graph and you analyze it. And then you process some more changes and so forth. And so we're also interested in dynamic patterns and anomalies. So this may be a pattern that changes in unusual ways over time. And so again, if you look at a particular static snapshot, everything looks fine. But if you start looking at it over time, you say, wow, this is changing in a way that I don't expect. So those are the 2 main things we're after, is the patterns and anomalies, and doing it in both static and dynamic graphs. So when you say the term graph mining, that can mean a lot of different things for different people. These are things you'll find in a data structures textbook of what cool things can we do with graphs. And these are probably a little bit more what most people think of graph mining. I won't go through all of these, but obviously I'm just going to focus on these 2. But there's a lot more that could be done. Okay, so here's the graph that has actually been on the slides, the last few slides. And now I'll let you, test your mettle as to see, can you find the normative pattern in this graph? Let's look at it. So, one thing you might say is, well, there's a lot of green nodes and there's a lot of purple nodes, et cetera. So yes, that's a pattern. But we're more interested in adding more structure. So you might start to notice that, well, I see a lot of purple and greens connected together. I see these triangles show up a lot. And with a little bit of thought, you can get to
Every single triangle is purple and green and blue.
yes. Yes, that is true. But if you go a little bit further and you extend it off of the blue, you see that it's almost always a red. And so, generally we're after, so that brings up a good question. So, here's two patterns, the one you pointed out, which is good. Here's one that extends it by a little bit, but there are some exceptions. It magically works. So like right here, that's an exception to this pattern. Sorry?
It's got a red one on it, on the blue.
Oh, it does. Okay. Yeah. So, yeah. So, I knew the answer. So, yes, this is an example of a normative pattern, but here's an example of one that is not normative. So, yeah, I guess I should have put a black circle around that one. But once you identify what you consider to be normative, then you can look for anomalies to it. But again, these are anomalies in the context of what's normative. So we would say, here is a close instance to our normative pattern, but it has a purple node instead of a red one. So how do we find these? And the general heuristic that we use to do this is based in the compression. So the idea is that, it's kind of like you want to take this graph, however you represented it, and you want to zip it up into, as few bits as you can. And so what's one way you could zip up this graph? Well, you could say, well, I see all of these instances of this pattern. So why don't I kind of replace them all with something like pattern one? And I call this pattern one. And now I can compress this graph and replace all of these patterns with like a single node that says this is pattern one, and a little extra information about how it's connected. And then the graph gets smaller. And so the question is, which of these do I prefer? Well, it's whichever one compresses the graph the best. So there's more instances of this. So we'd be able to collapse more of these triangles down to single nodes. But this one's larger. So, if we can get about the same number of those compressed, we'll get better compression than if we use just this triangle. So in our approach, which we call subdue, that's exactly what we do. We search through this graph looking for patterns, and we evaluate them based on how well they compress the graph, and choose the one that gives us the maximum compression. Okay, so a little bit more detail on how we do this. So maybe a little too much detail, but so how do you compress? You measure the compression of a graph. In general, if you get into information theory, there's a notion of description length, which is just if I want to represent some data, how many bits do I need? So that's the description length of that data. And then I can talk about the minimum description length, which would be of all of the ways that I could represent this data, which way is minimal, the fewest bits possible. And so if I have a way to measure that, then I can look at my pattern. Here S represents our pattern. And I can say, okay, I want to minimize the sum of the description length of the pattern because I have to remember what the pattern is, and then the graph compressed with that pattern. And so, the triangle will have a lower description length than the triangle plus the extra edge. But the graph compressed with the triangle, its description length is a little higher than the graph compressed with the triangle plus the edge. And so we search through the space of possible patterns and we evaluate them based on this description length idea. And whichever one minimizes the sum, that's the pattern we're interested in. And you might say, well, why that one? And all I can really say here is that we probably applied this to 20, 30 different domains, and from biology to social media, and in all of those cases, this heuristic seems to hold up in terms of identifying the patterns that we're most interested in. So that's the one we stick with. And one other thing to point out here is that, so say we have this graph and we identify this pattern that has these, in this case, it has 4 nodes to the edges, but we go ahead and compress it in 4 different places, but those places aren't exact matches to that graph. So that's actually something that we specifically put into our algorithm is kind of an inexact match. And so if the pattern matches is close enough, then we go ahead and say, yep, that's an instance of the pattern. It's going to compress it. And so then, so we might wind up with a graph like this where we compress those 4 instances, and then we can actually iterate over this and keep going. So now we can find there are 2 instances of this pattern of these 2 S1s with the purple and the green node, and so we can compress those down to this graph. And so you can keep iterating over this and kind of build a hierarchical pattern that ultimately compresses the graph down to a single node. So that's the approach that we use. So at this point, I'll let you do it, or you can watch me do it, to run subdue on a really simple example. But first, let me describe a little bit about what you're going to see. So, so if you want to do this on your own, you had some data and you want to represent it as a graph, then you're going to have to decide what the nodes or the vertices are, what the edges are, and you may need to decide whether the edges are undirected, meaning John knows Jane and Jane knows John, or they're directed, meaning that Jane works in the IT department, but the IT department doesn't work for Jane, something like that. So some relationships are undirected, some are directed. And so the general way we do this is, for each of the entities in the graph, those are vertices, we give them a number and a label. And then for each of the edges, they're either undirected or directed. We identify which 2 vertices they connect, and then we have a label on the edge. So this is a pretty simple graph representation. There are many other ways that you can represent the graph. But this is how we do it. So let me go through the exercise. So if you look in that exercise document, this is exactly what's in there. So first thing we're going to do is download the CSubdue system. I gave you a link on that web page, or the code is actually on that web page, but it actually lives on GitHub, is where it's normally available. Try this. So if you download the CySER system, downloads. Unzip it. And let's see. So first thing to do is to go into the graphs directory. And we'll look at this. So this is a really simple example where we have objects with various shapes, and those objects can be on top of other objects. And so the graph basically represents this picture. And as you might guess, the normative pattern we see is the triangle on top of the square. And so if you look in the data, you'll see vertices for triangle and square and objects, and then all of the edges are either shape or on. Yeah, not an insider threat problem, but a real simple example of what's going here. So if you go back to the source directory, so again, this is a C program or a lot of different C programs. And to compile it, you should just be able to type make. And then make install. All that does is copies a bunch of programs that it just compiled into this bin directory. So let's see, and then we back up one directory back to the CSubdue directory, and we're going to run subdue on that sample file. So subdue is now in this bin directory here. It's right there. So we're going to say bin subdue, and then the graph, of course, that we just saw lives in the graphs directory. So we'll say graphs, and then the actual graph. So when we run that, so it starts out, it prints a bunch of information about parameters. There are a lot of parameters you can set. But ultimately, it comes up with the three best substructures it finds. And this value is basically how much compression this pattern is giving us. And so you see the triangle on the square is the top one. The next two are basically missing one of the shapes. So here it's something on the square. And the next one is just triangle on something. So, and their values are a little bit less. So that's basically it. You represent your graph in this format. You run subdue on it, and subdue finds these highly compressing patterns. And the other thing that's part of this exercise is to visualize things. So this is where you need that GraphViz. I've already installed GraphViz here, but to do it, you would say yum, super user yum install GraphViz. Okay, so it says nothing to do because everything is already installed. But in your case, it would come back and say, should I install this stuff? If you say yes, you should get GraphViz in there. So GraphViz gives you a couple of programs. One's called DOT, which is a program that visualizes a graph expressed in dot format. And we'll also use one called SFDP, which is another visualizer that's a lot faster and can deal with larger graphs, which we'll use on our last example. But for this one, so I guess a couple of, well, we can just do the sample graph. So if we wanted to see what that sample graph looks like kind of to the algorithm, we can run this dot program on it to generate an image of the graph, and then we can see what it looks like. So let's say, so there's a couple of programs. There's this graph to dot, which will just take a graph and convert it to dot format. And then there's the subs to dot, which will take the output of Sudo and convert it to this dot format. And then the dot format can be translated into anything you want. In our case, we'll do images. So first, I'm going to convert that sample graph to dot format. So I'll do then dot, and I give it the sample graph. And then the second argument is the file you want to store this dot format. So if you want to see what this looks like, it's a textual format that just, you know, identifies the labels and the colors and the edges and their labels and colors and so forth. So it's a textual format. And then we can use this dot program, which is part of GraphViz, to generate an image. Like say dot, I give it the type, which I want. I'll do a PNG, you can do JPEG or whatever you want. And I give it the file. And then in this case, I'm going to use a Unix idiom, which is redirecting the output to a file, is what this greater than means. So I can put any file I want out here. Let's sample.png. And then I'll navigate over to that. And then download. So I don't know what image viewer that is, whatever comes with this distribution. There you can see more standard graph. You don't see triangles and squares anymore. You just see the labels. But that's obviously what is more like what Sudo is dealing with to try to find these patterns. And then the other thing you might want to do is to visualize the output. I mean, the output's pretty obvious. It's triangle on square, but you can also visualize that. But to do that, exit out of here, you have to run Sudo and tell it to output the pattern that it learned to a file. So go back to so here's the command we use to run Sudo, and I'm just going to add out. So I ran it with this dash out, and then I gave a file name. So the substructures or the patterns that are learned will go into that file. And then once again, I can use the graph or that subs to dot to convert it to dot and then visualize it. So let me do that. So that created, oops, sorry, rerun that. It should be dot. And then I can run dot. Sorry, this should not have the greater than. So the second argument is the file to write to. So. Okay, some misspellings, but bear with me here. So I called it sub.gs for some reason. G, and then the second argument will be subs dot. Okay, so that wrote the substructure to the dot file, and then we can convert it to an image. Then that image. And so we get our object on object. This top object is shaped triangle, bottom object shaped square. So I know that's pretty simple, and it's also pretty tedious because it's all command line. But we're researchers, we're not developers, so we're more interested in what goes in the code than making it easy to run. But someday we should have a GUI to do all this. One of you can do it. So I think that's all of exercise 1. Again, that gives you an idea of how you can run subdue on a graph and identify the highly compressing patterns that are in the graph and then visualize them. Which is kind of what we do all the time. Okay, so now I'm going to switch back. Any questions? Everybody? Okay, so that was exercise 1 we just went through. And so a few other things that you can do with subdue. One of the things that you might want to do is give it some training. So for example, if you say, there's a specific pattern I want you to learn, and here's some examples of graphs that have that pattern, and here's some examples of graphs that don't have that pattern. You may not know exactly what the pattern is. You just say, here's a graph of my organization on October 3rd, and here it is on October 4th, October 5th, October 6th. On October 7th, we had a breach. So this is October 7th, et cetera. So you can say, these are positive graphs, these are negative graphs. And if you tell subdue that a graph, you have some positive negative graphs, then it won't look for just the graph that compresses this, but a graph that compresses this and doesn't compress that. And so if you can find such a graph, then that is a way you can distinguish between these two and perhaps even use this as a signature, saying, if you see this, then it's normal. If you don't, then it's not normal. And all we do is, remember, this, we can put description link here, but we basically say the substructure compresses the positive graph well, but it doesn't compress the negative graph very well, which would mean that this ratio would be low. And so if we find the substructure or the pattern that minimizes this ratio, then that pattern will tend to be ones that are in the positive graph, but not in the negative graph. So again, if you have some supervision that you can apply, then you can direct subdue a little better. So If you want to try that out in the graphs directory, there's another graph called groups.g, which is some social groups that exhibit a pattern or don't exhibit a pattern. And you can feed that into Subdue, and it'll notice, you'll see little XPs and XNs in there for positive and negative examples. And it will, again, learn a pattern that discriminates between the two and doesn't necessarily just compress this composite as well. So a little bit of applications that we've done over the years. This was a project for DARPA that migrated to the Air Force. But the idea was, we're basically, in this case, we're going into an area, a region of the world, and we're trying to win hearts and minds. And so we want to identify people that are, on our side, so to speak, and people that are not. And so as we identify various people that are in our positive or negative class, then we can represent them and their social network, kind of like we did back here. So these would be, people that like us, people that don't like us, or vice versa. These are people that don't like us, and these are people that like us. And we're trying to find patterns that would allow us to identify which category is somebody in. And more importantly, how can we get somebody into our category? So basically, if I can get rid of this yellow node from the person's social network, that might bring them over into the other category. So we did this on some data collected, simulated data collected from simulated environments, and showed that you could do this. Give it that. Another thing that you can do with Subdue that we kind of mentioned already is that you can keep running it. So once you run it once, then you can tell it to compress the graph with the pattern it found and then run again. And so you do that by supplying this iterations option, and you can tell it how many iterations you want. I think if you give it 0, it'll iterate until it can't compress the graph anymore. And so if you run it on that same sample that we just played with, you'll see this come out, which is, you can see that it still finds that triangle on square structure, but then then it compresses that away and looks for more patterns. The next pattern it will find is the circles, which are obviously not part of the triangle on square pattern. And then the third pattern it finds is actually built from the first pattern. So it's basically the first pattern with an extra object on it. If you remember, it was drawn. So here we have the triangle on square on a rectangle. And so it's picking up on the fact that it can find the triangle on square on something. And so it can keep iterating until it's basically compressed as far as it can go. And then you get this kind of hierarchical explanation of the patterns that are in your graph. And that can be more useful than just trying to find the single best one. And so another project we did, again, a lot of our projects are basically finding groups of good people and bad people and trying to figure out how to tell them apart. So here's a couple of terrorist networks. I think this is Al-Qaeda, maybe that's Al-Qaeda, and Vermont and so, basically it's a social network of the people, which are most likely the leaders and their affiliations. And so in this case, we're trying to figure out what's the typical structure of one of these terrorist networks. And we just have 2 of them. But when we run Subdue in this iterative approach, we keep compressing, it finds a very rich structure. I kind of expanded it all out, but if you actually saw the structure, it would basically be like, this is sub 1, this is sub 2, this is sub 3, we've got a sub 1 connected to the sub 3, and that's connected to sub 4, et cetera. But if you expand it all back out, you can start to kind of see what the typical structure is of one of these terrorist networks.